In the months before April 2010, BP pushed to finish a deepwater exploration well called Macondo, drilled far offshore in the Gulf of Mexico. It was not a simple hole in the seafloor. It was a narrow path into high-pressure rock where every step depended on heavy drilling mud to keep oil and gas under control. But the well fell behind schedule. Days turned into weeks, and each extra day offshore cost a fortune. As the delays mounted, the project's center of gravity shifted. The job still demanded precision, but the clock started to matter as much as the geology. Plans changed, then changed again, as crews dealt with stuck tools, unstable zones, and sections of the well that did not behave as expected. Each problem forced a choice: pause and spend more time, or adjust and move on. That pattern quietly set the tone for everything that followed. By early April, Macondo carried a reputation on the rig and in the offices on shore. Difficult, expensive, and overdue. That pressure did not look like a single reckless order. It looked like small decisions made under strain: how long to wait, what to redo, what to accept. The goal became finishing the well and moving the rig to the next job. When time became the enemy, risk started to feel negotiable. That was the trap. With every day of delay, the well plan kept shifting. Engineers reviewed options for how to finish the hole and seal it off, and the choices came down to two paths, one that added layers of protection and one that saved time. The faster route trimmed complexity. It also trimmed flexibility. Once those decisions locked in, later problems had fewer ways out. The schedule stopped being just a target. It became a force. The casing plan tightened around a long production casing, run in one continuous string instead of breaking the job into stages. It meant fewer trips, less equipment, and a quicker finish. But it also meant the cement job had to work almost perfectly the first time, across a long section in a narrow space. There were fewer chances to confirm isolation, fewer places to catch a mistake, and fewer options to repair it without major delays. As that design took shape, safety margins shifted from being layered to being concentrated. The well depended more on a single seal at the bottom, on a clean cement placement, and on the assumption that small warning signs would not appear later. Each step still looked defensible on paper. Together they reduced tolerance for error. A slower plan carried redundancy. The chosen plan carried urgency, and urgency did not forgive uncertainty. The operation shifted into what sounded like a simple phase: temporary abandonment. The well had been drilled and lined, and now it needed barriers, so oil and gas stayed trapped far below while the rig moved on. The plan centered on cement at the bottom of the production casing, sealing the space between steel and rock. On paper, that cement became the foundation of everything that followed. To do it, the cementing job was contracted out and scheduled like any other service step. A specialist crew mixed a tailored slurry and pumped it down the casing, aiming to push it out into the annulus and lock the well in place. The details mattered. The design had to set fast enough, bond tightly enough, and resist pressure from the reservoir, because once it hardened, no one could see what it actually did. That was the quiet risk inside the plan. Cement looked like a final answer, but its quality lived at the bottom of a mile of pipe beyond direct inspection. If it channeled, if it failed to bond, or if fluids slipped through before it set, the well still had a path. The work was executed, the barrier was assumed, and an unseen integrity question remained, waiting for the next step to expose it. The rig shifted from building the well to getting ready to leave it temporarily sealed. That sounded routine, but it forced a long list of coordinated steps, and every step took time. So the plan tightened. Heavy drilling mud that had held pressure down would be pushed out and replaced with lighter seawater, but the exact way that displacement happened got adjusted to move faster and keep the schedule from slipping again. Those adjustments changed more than timing. They changed what the crew could easily see. When heavy mud was displaced, the well's behavior had to be watched closely because small pressure changes and small volume gains were the earliest clues that something was wrong. But monitoring practices were streamlined, checks were spaced out, and some attention shifted to other tasks that also had to be finished before departure. On a deep water rig, warning signs rarely arrived as a single loud alarm. They arrived as mismatched numbers, a tank level that did not quite make sense, a pressure trend that looked off by just enough to doubt it. With procedures optimized for speed, those weak signals became easier to explain away, easier to miss, and harder to challenge. The well had not failed yet, but the margin for noticing failure had shrunk. The next step sounded simple. Prove the well was sealed before replacing heavy drilling mud with lighter seawater. That proof came from a negative pressure test. Crews reduced pressure inside the well and watched to see if anything tried to push back in. If the barriers held, the pressure stayed steady. If oil or gas had a path, the gauges told the truth. This test was supposed to be a final checkpoint. It became a turning point. The first readings did not line up with what a sealed well looked like. Pressure behaved strangely, and numbers stayed higher than expected. The result did not fit the pass criteria, and it did not match the story everyone needed to be true. Instead of treating the mismatch as a warning, the test got rerun and reframed. Attention shifted toward explanations that made the data feel harmless. The test result moved from uncertain to acceptable without the well actually changing. That judgment created something powerful: confidence. Once the test was labeled a pass, the well was treated as stable and under control. Plans that depended on a secure seal now seemed safe to continue. But the anomalous readings had pointed to a leak path that still existed. The barriers had not proven themselves. They had only been signed off. From that moment on, every next action rested on an assumption, and that assumption was wrong. The crucial change began when heavy drilling mud got pushed out of the well and replaced with seawater. That sounded routine, but it removed pressure that had been holding back the reservoir. With less weight in the wellbore, oil and gas started slipping past the barriers below and moving upward. At first, it did not roar, it crept. But every minute of displacement gave the hydrocarbons more room to expand and more speed to climb. Up on the rig, the well did not announce itself with a single alarm. It hinted. Flow and pressure readings began to drift away from what the crew expected during a controlled displacement. The pit volume system, meant to show how much fluid stayed on the rig, started to show gains instead of losses. The returns coming back from the well did not match the pumps. These were early fingerprints of a kick, formation fluids entering the well. This was the first real-time moment when the developing blowout still could have been stopped. If the influx got recognized for what it was, the response could have been immediate. Halt the displacement, shut in the well, and use the equipment designed to contain pressure. But the well kept flowing while the signals got explained away. Hydrocarbons continued rising, expanding as they came. The window for a controlled fix narrowed with each passing measurement. On April 20th, 2010, the flow that had started quietly stopped behaving like a manageable problem. As lighter seawater replaced heavy mud, pressure inside the well pushed back harder than the crew expected. The rising hydrocarbons gained speed, turning a subtle influx into a surge. Instruments showed the well coming alive, but the window to correct it narrowed by the minute. At that point, the well no longer needed help to get worse. The surge raced up the wellbore and expanded as it rose because gas took up more space as pressure dropped. That expansion drove the blowout faster, forcing mud and gas toward the surface in a violent column. The crew tried to respond, but the physics moved quicker than human reaction time. The blowout preventer, meant to shut the well in an emergency, did not stop the flow. Now the hazard reached the rig itself. Gas broke onto the rig and found ignition sources that existed on any working industrial site. Explosions followed, then fire, and the situation changed instantly from a well-controlled emergency into a life-or-death disaster. Systems that supported normal operations were no longer the priority. Survival was. The blast and flames cut off escape routes and damaged critical equipment, making control efforts even harder. In minutes, a project problem became a deadly catastrophe. By the early hours after the explosions, staying on Deepwater Horizon stopped being a rescue option and became another risk. Crews evacuated into lifeboats and onto nearby vessels as the fire kept feeding. With the rig still connected to the well by the riser, everything remained under tension: steel, pressure, and time. Then the structure began to fail. The platform did not just burn, it started to come apart. As the rig drifted and sagged, the riser line bent and tore. That break changed the emergency from a surface fire into an open pipeline from the sea floor. The blowout preventer stayed down there, but the well kept pushing oil and gas upward through damaged paths. Operators could no longer control what they could not reach. They could not shut valves by hand. They could not pump heavy fluid down from the rig. The well flowed on. On April 22, 2010, Deepwater Horizon sank. It disappeared beneath the surface, and the focus shifted to what remained below: alive well releasing hydrocarbons into deep water. Oil did not simply rise like a single plume. It spread, broke into droplets, and moved with currents that most people never thought about. The spill became harder to track and easier to underestimate. A new reality set in. This was an undersea blowout, and it was growing. For weeks, the response moved from one improvised fix to the next. Engineers tried to control the flow at the seabed with devices and procedures that sounded simple on paper but failed under deep water pressure. Some attempts made the situation worse by adding uncertainty to an already damaged system. Each day, the oil kept coming, and each setback narrowed the options. The priority shifted from stopping the leak quickly to stopping it safely. Eventually, a new cap sealed the top of the damaged equipment, and the visible plume slowed, then stopped. But shutting in the well did not end the danger. Pressure inside the well rose, and crews had to confirm the casing and surrounding rock held together. Then relief wells intersected the original wellbore, and heavy drilling fluid was pumped in to push the hydrocarbons back down. Cement followed. The well was finally killed. With the flow ended, attention turned to why it happened at all. Investigations traced the disaster to a chain of breakdowns, not one dramatic mistake. People misread tests and accepted weak explanations. Teams worked with blurred roles and rushed decisions where schedule and cost carried quiet authority. Safety systems relied on assumptions that went unchallenged. Oversight failed to catch the growing risk. The blowout became the outcome of compounded human organizational and regulatory failure. After Deepwater Horizon, offshore drilling did not just restart and move on. It came back under tighter rules, heavier scrutiny, and a clear demand for proof, not confidence. Regulators required stronger well designs, clearer documentation, and more independent checks. Companies rebuilt their systems around barriers that had to be verified, not assumed. The old pace still existed, but it no longer stood alone as the main measure of success. On rigs across the Gulf, safety changed from a set of procedures into hardware, training, and constant testing. Blowout preventers faced stricter standards and closer inspection, with more focus on whether they actually worked under real conditions. Monitoring and well control practices became more formal, with clearer triggers for stopping work. Drills, audits and reporting grew routine. The industry treated the last minutes of a well as a danger zone, not a victory lap. But the disaster left costs that no new rule erased. People died, families carried it, and communities along the Gulf lived with the disruption for years. Oil and dispersants affected wildlife and fisheries, and long-term impacts remained contested and uneven. Lawsuits and settlements moved money, but they did not rewind time. Deepwater drilling continued, yet the mindset changed. What once felt like a normal rush to finish now carried a permanent warning.